using the search string cat or, in brackets, dog, not horse, returns all pages containing cat or whatever on the other end, and that would have dog without horse. So these kind of things. Okay. Examples, let's look at further. Here are 4 web pages. In the page 1, dog. Page 2, cat and horse. Page 3, dog and horse. And page 4, all 3 of them. So if we use a particular string, okay, then see what we find. If we are looking for cat, there's or in between. Dog, not horse. Do you think what pages would show up?
1 and 2.
I want you to think. 4. And hardly anybody thinks the computer is on.
That's
1, 2, and 4. Right in front of you. Come on. It doesn't make sense. Right. Answers.
1, 2, and 4.
1, 2, and 4. 4. Can you justify that? Can you say why?
Because 1 has dogs, not horse, which is 1. 2 has cat, so it doesn't matter if it has a horse or not. And the same as 4. It's cat, so whether or not it has horse or dog doesn't affect which is included.
What's your name?
Adam.
Adam. Adam says that the answer is 1, 2, 4. I disagree with him. How many of you agree with Adam and how many of you agree with me? So people who agree with me, can you raise your hands? 1, 2, 3, 4, 5, 6, 7. Anyone else? 7.5. And the rest agrees with Adam. If you agree with Adam, you will have to justify that. Now, this is actually fundamental. I'm spending time on it. If you understand what we really mean by or, and in this connective, and that connective, we're nearly done. Okay? So you really have to understand there. Actually, I was wrong. Adam is right. Absolutely right. There. One of the things that you're looking for, think of that. Okay. Firstly, it says there's an or statement in between. So if a box has cat, don't look for anything else. This box has cat, that box has cat. So these 2 and 4 are definitely there. Now we look for this statement. Dog, not horse. Yeah? So it has to have dog, but not the horse. So this one has dog and there is no horse in it. Okay? And this one has dog and horse both, so it does not satisfy this criteria here. So that's why 1, 2, 4 are correct. Okay? Let's look at next. Cat or dog, either cat or dog, but not horse. Now, not is outside the bracket. Carefully think. We have this statement and it's connected with that statement through this connective not. So what you think should be the answer? 1. Can you justify?
Everything but 1 has got horse in it, which is being rejected by the not operator.
Fantastic. Yeah, that's absolutely right. Okay. This example shows that the the positioning of brackets in the search engine matters. Okay, connectives matter. A logical puzzle. There are lots of puzzles one can ask. Think, if you're in a village where there is only one barber, and barber shaves those people who don't shave themselves, only, who can't shave themselves, then who shaves barber? That's another puzzle. But the puzzle that I'm going to explain here, you're in an island, and it's inhabited only by knights and knaves. What's a knave? I don't know. You tell me. Anyone else care to explain? Everybody knows knights. Knaves.
Well, can I answer female ones?
So I think knaves are warriors. I think
Precise definition, to be honest, I don't know. Okay? I always rely, I thought there are just two people. Knights who always tell the truth and knaves who always lie. You can attribute that knaves to anyone you like. But, a dishonest or unscrupulous man. I don't know why it's a man, but it could be anything. Okay, I have not looked at the reliability of that source yet. I just for my information. I would think these are just person A and person B. Okay? That's a good thing about maths. You know, when you do maths, you don't care about other things. You just look at the truth values. Nothing more than that. Knights always tell the truth, and knaves always lie. Okay. You meet two inhabitants, A and Z. Here is that. It says we are both knaves. Now you already got the puzzle, right? Okay. Now think of that. If it is saying that we are both knaves, but they always tell they always lie. So they can't be knights anyway. Oh, okay, hang on, what is happening? It might always tell the truth. So, can you determine what Abe and Zach are?
Zach is a knight.
What?
Zach is a knight.
Zach is a knight. How do you know?
Well, if they were both knaves, they wouldn't get to it sort of lie. So Abe would have to be a knave to lie instead of they're both knaves.
They could both be one, but I don't think
They always.
You're thinking it's actually okay. I'm inclined to that.
If they're both knaves, so they can't both be knaves.
So Abe is giving a statement, not Zach at the moment. If Abe is giving a statement saying that okay, we are both knaves, it is possible that she herself is a knave and lying. The other person might be truth who has not given any statements yet. But anyway, this is not the purpose here. It is just I'm saying that there are puzzles. Okay? Puzzles of this type were made popular by the American logician Raymond Summerlin in his 1978 book titled "What is the Name of This Book?" Okay. In this subject, we don't have time to go through the puzzles. We don't want to find their truth value. We just want to look at the criterions that may determine truth values. We are learning to the focus of artificial intelligence and all that. That how if an information is given, how are we going to find their truth values and all that. Okay. Propositions. But to this end, I would introduce few terms here first, and then we try to connect those terms with the help of some symbols. In arithmetic, we work with numbers. Similarly, in fundamental logic, we work with propositions. Proposition is a statement which is either true or false. Okay? So a proposition is a statement that is either true or false. Whichever of this is the case is called the truth value of the proposition. We are not concerned with actual truth value. We are just we're looking at statement and see that whether it could be true or false. If that happens, then we call them as propositions. Examples: there are 200 cents in a dollar. It's obviously wrong, but it's a proposition. It's false, but it's a proposition. 2012 Olympic Games were held in London. It's either true or false, but it's telling you a fact. Okay? It's a proposition. Do you think it's true? Yeah. Good. Who won the 5,000 meters there? Move for Okay. Right. 3. The assessment for discrete maths consists of one exam and 2 tests. It's true. But irrespective of that, it's either true or false, so it's a proposition. To pass discrete maths, you must gain a mark of at least 50% on the exam. Is it true or false?
True.
One person said true. Anyone else?
You also need to get something else, what is it, 50% of all your assessments. So, like, it's not the full statement.
Come on, nobody read the subject learning guide then. The most important document that I gave you, you didn't read it. No, you have to get collective 50% marks. You don't have to get 50% in the final exam. If out of 35 marks that you would have in tests, if you get 35, let's say full marks, then you only need 15 marks in the final exam to pass, which is 15 divided by 65. It is close to, you can see what percentage that would be. Right. Okay. Number 5. Every even number greater than 2 is the sum of 2 prime numbers. Do you think it's true? Let me write it down. I can write 7 as 2 plus 5, sum of 2 primes. Okay? But I want every even number, so this is wrong. So let me write it down as 8. I can write it as how?
3 plus 5.
3 plus 5. Well done. And similarly, you can think of any other number. 14, for example, is that 7 plus 7. Wow. Good. So, do you think this statement is true? Yes. Okay, good. Anyone else saying yes? We don't know. We really don't know. Because we said all even numbers. We don't have a proof yet. We have a proof for sum of 3 primes, that every even number can be written as sum of 3 primes, but we don't know the proof that every even number can be written as sum of 2 primes. Okay. Now, coming back to the topic, with regard to truth values of 2 and 3 are true, 1 and 4 are false, 5 we don't know. But it's definitely true or false. We call it a proposition. It's still a proposition. We don't know exactly whether they are true or not, but either one of them is true. Either it's false or it's true. Anything could happen with that. Okay. So it's a proposition. So all of these 5 are propositions. two of them are true, two of them are false, one we don't know, but we believe it's either true or false. That's a proposition. Can you give me an example of things which are not propositions?
Questions?
For instance,
What is the sum of 2 and 3?
yeah, that's right. What is sum of 2 and 3? It's a question. It's not a proposition. There is no true or false answer for that. Anyone else? Any other examples?
What about a prime binary to modulus? That's either true or false, isn't it, as well as being a question?
What do you mean binary to modulus?
So, prime 1 to base 2 modulus, that's a question, but
Oh, yeah,
it's
yeah,
going to
sure.
be true or false because it's in binary.
But you can always find binary representation of a number. So it's true or false. But the
prime
thing is,
modulus,
the thing is whether you are stating it in a way that only asks for true or false values, or give only true or false values, or there is something else. So let me give you more examples on that. For example, you can give a command, or you can point out to some fact. This is a whiteboard, for example. Yeah, it is a whiteboard. Yeah, sure, it's a command. So, well, the conjecture is, Goldbach conjecture is about that can you write every even number greater than 2 as a sum of 2 primes. It's after a German mathematician, Christian Goldbach, and proposed this conjecture. Conjecture means open problems, all right? So whose answer we don't know. He actually proposed problems that every number greater than 2 can be written as sum of 3 primes or sum of 2 primes. Someone has already proved 4 or 5 years ago, Harold Helfgott proved that, okay, you can write sum of 3 primes, any even number greater than 2. But sum of 2 primes is still open question. You can test this conjecture on the web, however, it has been verified that it is true up to this decimal place of a number. Up to that much big number, it's been verified that it's true. What happens beyond that? That was in 2012. At the moment, this number is probably close to 30, but still it's finite. We want to prove it for all. And when you want to prove something for all, you have to give a general proof. And that's why it's still an open question. You can get $1 million if you can prove it. Very easy to state, so it's an open question. Okay. Right. Examples of non-propositions. Stop talking. Right? It's a command. Right. What day of the week is it today? This is a question, not a proposition. This sentence is false. Self-referential statement. So if a self-referential statement, you don't have to worry about their truth values. So it might seem like a proposition, but problems occur when you try to determine their truth values. Okay? So when there is self-referential statements, we would not consider them as sort of propositions. Paradoxes. Okay, this sentence is false is an example of a paradox. You know what a paradox is. If you think it's true, but the statement itself saying it's false, something like that. So, for example, here, so if you want to determine its truth value, this sentence is false. If the sentence is true, then the sentence is telling us that it is false. If the sentence is false, then the information it is telling us is false. So, in other words, it's complement of a complement that has to be true, right? Like a friend, right? No? Okay. Paradoxes. So this is an example of a paradox. Paradox causes difficulties if we allow them to be propositions. To avoid potential problems, we won't allow any statement that is self-referential to be a proposition. So that's in our head. If it's a self-referential statement we encounter, we would not deal with them when it comes to proposition. So this sentence has 5 words, although it is true, it's self-referential. It's not a proposition. We'll not consider them. Sentences such as winter is cold, football is boring, these beliefs this depends on personal beliefs. Someone might like them, someone might not like them. So we will not regard them as sort of propositions in that sense, because this varies from person to person. We want to look at something which are universal. Okay, predicates. Why? This is an example of predicate. It gives you list of numbers. Okay. Why less than 3? It contains all those numbers which are smaller than 3. So this depends, the truth value of this statement depends upon when you give the value to y. What I mean there is, if y is 2, then this statement is true. If y is 4, this statement is false. Okay? So this is an example of a predicate. We'll be looking at predicate logic later in our work. And yeah. So what will we study in logic? In logic, we will not study the truth value of a proposition, such as the 2012 Olympic Games were held in London. We will not look at the truth value. However, we will consider a systematic way of determining values. Right? Okay. If it was true, then what happens? If we are going to connect two propositions, what are all the possibilities? Okay. Instead, we will study propositions such as, if Mary and Michael are not both left-handed. Now, you can see that this is sort of a puzzle. I'm saying two persons, Mary and Michael, are not both left-handed. If I'm saying this, one statement, then I'm implying from it. From first statement, I'm saying there are two people who are not both left-handed. Then what that implies, this is the implication, that Mary is not left-handed, one of them is true, or Michael is not left-handed. So we don't have to determine actual truth value, but we have to look for, from one statement, how one statement implies other two statements. What are the possibilities?
How do you know both of them aren't left-handed?
No, I'm giving. In one proposition, you are given that, okay, given a fact, that if, now there is a if, right? If both of them are not both left-handed, so at least then there is one possibility that either Mary or Michael are left-handed. Right? One of them is left-handed. So if the statement, if you modify that statement with, if you put or there somewhere, or if you modify that, then you have to draw conclusions from the first proposition, from the first statement. That kind of thing that we'll be doing. Okay. So you can see that this is a true proposition, all of it. We'll learn methods to write them in symbolic form. Okay. So the following proposition is also true. If 57 and 59 are not both prime numbers, right? You can see that both of them are not prime, actually. Then either 57 is not a prime number or 59 is not a prime number. So this is also a true statement. 57 is not prime, it's divisible by 3 and 19. Do you agree with that? So 57 is not prime, 59 is prime. And the proposition first statement is saying if 57 is telling the truth or fact, if 57 and 59 are not both prime numbers, then one of them is not prime. We don't have to determine that one of them, which is 57, is not prime. We don't have to determine that. We don't just only have to look at the conclusion. At the moment, as I said, we are making some grounds for actual work to start later when we start dealing with symbols and we try to write these kind of propositions in form of tables and finding their truth values. Okay, return to the proposition. Now we'll try to write them in sort of symbolic form. If Mary and Michael are not both left-handed, then either Mary is not left-handed or Michael is not left-handed. This is called a compound proposition because what you are doing, you are writing them in sort of a combination form. There is one proposition here, and you are connecting it with another proposition. Basically, within this, there are again two combinations of two propositions. Mary is left-handed is one, Michael is left-handed another one, and these are connected together by word and, not, then, if, or. So these are the words which connects a statement with another statement. It is built up from atomic propositions. Atomic means single. Mary is left-handed and Michael is left-handed using words and, or, not, if, then. We will not write, later we will not write them in words. We would write them in symbolic form. There will be specific symbols for them. We'll come to that. These words are called connectives. In logic, connectives play a role similar to those of operations such as addition, multiplication in algebra. In the previous section, we worked on arithmetics. There we dealt with numbers, so we did operations like addition, multiplication, subtractions, and all that. Now we're dealing with logic, and in logic we deal with connectives. Connectives have the same meanings as would have those arithmetics over there. So let's look at notations for basic connectives. There will be 5. These connectives and their symbols are, for AND, we will use this symbol, and this is like a lower V, or is upside down V, is the right V, just like that. Not is this symbol. If then is this symbol. Sometimes people also write it like this, implies, okay. But here we don't use that notation. And this means, the last bit means if and only if. So if one of the statement is true, then the other statement is true, and vice versa. So it's both ways. Okay. All right. So these 5 connectives we have to use, and we'll use them frequently in the next 2 weeks. All of that. So just keep that in your head. Okay. So if and only if also is equivalent to, or if and only if. Okay. Now, before we conclude, another logic puzzle, and see if you can arrive at the truth value of this logical puzzle. Okay. But before that, let me actually see how many of you remember those connectives. What was the connective for AND? This one? Mm-hmm. And what's the connective for NOT? Pseudo. Connective for OR? Is that right? Yeah. If then? And if and only if would be both ways. Yeah? Okay, let me scratch your head then. And we move, I take you back to the puzzle. can you write it down in terms of those symbols and see what you get? We will be doing this in the next lecture anyway, but just a text that I want to see that you are thinking the same way as it should happen. So think of that, if Mary is left-handed is your proposition P, Michael is left-handed is your proposition Q. Then how you write this in this symbols form? Okay, what you got? Look, in the statement we said, if Mary and Michael are not both left-handed, and I'm writing it as Mary is left-handed, Michael is left-handed. What you got? So you're saying Michael is left-handed, Mary is left-handed, and Michael is left-handed, but not. Okay, so what that would imply?
No, or it's left-handed.
Okay. Okay. What's your Well, there you notice something. And is a binary connective. It connects two propositions, two statements. Or also connects two statements. Not is a unary operator. It only applies on one statement. Okay. And again, this is a binary and that is also binary. So you started off, if Mary and Michael, so there is an if statement, so there has to be this thing somewhere, if then. And here, you're saying Mary is not left-handed or Michael is not left-handed. So not, Mary is left-handed is P. If I put not there, that means Mary is not left-handed. Or Michael is not left-handed. So this is the implication of a statement which I still have to write. In the first half, it says, if Mary and Michael are not both left-handed. So you pull the not out because it's a unary statement. here I'm saying Mary is left-handed and Michael is left-handed. No. You would have watched Borat, right? Have you? No. You haven't watched Borat?
I have, because I was saying not, but
Yes. Not in the end. So that not is in the end. But don't apply that joke somewhere here. There is no Pamela Anderson around. If you have not watched it, then you won't understand what I meant. Sorry.
I won.
What?
I won.
No. All right. Okay. Well, where were we? These kind of things we will be after. So this is the symbolic logic that we're using it. Slowly. So based on that, we will be converting these kind of propositions into these kind of symbols. This is how search engines would work. With these connectives and or how they converse to multiple engines. Right. Let's move on. I'm giving you last puzzle, and you will be given maybe 15 minutes for that, and see what you get from it. Now recall the island of knights and knaves, where knights always tell the truth and knaves always lie. Okay? Now, you met 3 inhabitants there. On a recent visit to the island, I met 3 inhabitants, A, B, and C, and was told that at least one was a knight. The fact is, at least one is a knight. At least one is knave, and one of them had a prize that I could have if I could determine which one had it. That's the question for you.
So we're just doing a single question task, or?
This is for you. Can you?
There's one more part of the chapter actually showing up on the board.
Don't have to see that. Do you have to see that? Really? So the three made the following statements. You don't have to see that to determine the truth value. I intentionally stopped there so that you think about it. Okay? The 3 made the following statements. A, I have the prize. B, I don't have the prize. C, B doesn't have a prize. Which one has the prize? So you should have asked this question right here. You don't have to go for these. You can change these values anytime. So if there are 3 inhabitants, at least one is knight, at least one is knave, and one of them has a prize, something like that. And what you can see, you can start going that, okay, if one of them is this, then what kind of possibilities are there and all that. Yeah. Okay, now, if you want to proceed with this question, okay, tell me the answer.
C.
I don't know. I have not calculated it, so you have to justify that. Can you justify?
Yeah.
Oh, go ahead.
Okay, so A says I have the prize, but it must be lying because B says I don't have the prize. So if it was the name.
So if you think, okay, you started off as B is a
B must be a knight.
knight. Okay. All right, let's see B is a knight. Okay. Then
B then that means A, you can't be the knight. And
Why?
Yeah, because B's a knight.
No, at least one is a knight.
Yeah, yeah.
Oh,
Oh,
there has to be an extra knight or an extra name.
yeah. I think that was at least. Come on, right?
Is the word at least.
I think
It's possible that there are two knights, so it's possible there are two knights. If you can determine who are knights or knight, then pretty much you're done.
I can see it now. B's and
It
A.
must be one of each.
There has to be an extra.
Yeah, it's what's the same. So A's also A's a name.
No, the gap. Oh, look. There's a 33% chance you're true, right? If you just shoot an arrow in dark, there's 33% chance you'll hit the right target. I want only first go and you give me a right answer with justification. That's the
I've got it. Alright. So A and C are knights and B's and A. If
I don't know.
okay. I didn't know if I can run it out.
You have to write it down. You have
Okay.
to write it down and justify.
I don't know if I can write it down the way we were just doing it. But okay, A is a knight.
A is a knight, let's say.
A is a knight, he's telling the truth, and C's telling the truth. Okay,
So that means A and C are knights.
But that would make B and A. Actually, no, don't worry.
Yeah, there has to be.
I thought I had that one.
Who was the one that said that there was at least one knight and one knave?
It's in the question. It's a
So
fact.
It's
a fact.
Yeah, okay.
Yes, give it. You have it?
no.
So it says there's at least one knight, at least one knave, and at least one person has a prize. That means there's one of each.
There are only knights and knaves on that land.
Okay.
No, I do have it.
Oh, you do have it now. Okay.
Yeah.
I messed it up. So A has to be a knave because if B was an
So A has to be knave. That means A does not have the prize.
yeah, A doesn't have the prize. Because if A was a knight and it had the prize, then B would have to be a knave saying I don't have the prize. Okay, I know that A's a knave. I can't explain it in words. Like 100% A's a knave.
Yeah.
B and C.
If you start with A and go, say, if you run different two scenarios, say A is telling the truth, then B would have to be saying false, and C would have to be.
Of course, there are all different scenarios you have to look for, and ultimately there is an answer for this.
I would say A is a knave, and the other two are not. Meaning that. I would say C has the prize.
You were saying something.
So, B and C are disagreeing with each other, which means one of them has to be a knight and the other one has to be a knave.
B and C aren't disagreeing with each other.
They're agreeing with each other.
Then
Okay. Yeah, and well, it means they either have to be both knights or both knaves.
which means A has to be the knave. Wait, no,
Okay.
A does have to be a knave. I worked it out before.
Yes, A can't be
If
a
you
knight.
just turn the question around, so who doesn't have the prize, the two liars are going to either point to the same person or the truthful
That's
person.
another way of looking at it.
Yeah. So A has to be a knave because
Okay, you are saying A is knave. That means A doesn't have the
A
prize.
doesn't have the prize.
Okay, gone.
C has to have the prize because C would be a knight, saying that B doesn't have the prize, and B is saying
Yeah.
he doesn't have the prize.
Yeah, exactly. Yeah.
Okay, so you are saying C is a knight.
Who has the prize?
Yes, he is not given. Okay, for the time being, there is no wrong statement yet. So B doesn't have the prize. C hasn't lied yet.
Yeah, exactly.
Okay. Now coming to B then.
If he was a knave, he would say I have the prize.
What?
If if he had the prize and he was a name,
Uh-huh.
never mind. He would say, I don't have the prize. Absolutely correct.
Then that's lying, right? Then he has a prize.
But if we can safely deduce that A is a name, then it means that B, that, yeah, I knew where I was going with that. What's that?
But like, there might not be a prize as well because the person who says
No, it's a fact in the question. So the question is whether Nate told you the question.
no, yeah,
No, the fact
the
is
name
that-
told you.
okay.
He's one thing.
If you're getting the question, why would you have to question? Why would you be going for the his information if you get the question? What even is the question?
The thing is, if A is
Now you see, everyone liked this topic,
So
right?
if the knave told you that one was a knight and one was a knave and that someone has a prize,
We are not questioning who has given this question to you. Think of that as a fact.
oh, okay, yeah.
When it comes to puzzles, think of them as facts. And then after that, you have some set of conditions given to you. Within those conditions, you have to work out.
If
I don't know the answer.
C has
I'm inclined to C, but I want your justification.
I think it's C because if B and C are both knights and they're both in the truth, because they both have to be the same because they're really each other. So if B and C are knights, then A is lying about having a prize, and B can't have a prize because the knight's not the truth, so it has to be C. However, if B and C are names, that means A must be the truth, which means that A has the prize and B has the prize. B is lying about saying.
No, two people can't have the prize.
So therefore, B and C must both be knights, and A must be the knave, and C must have the prize.
Yep. I agree with you there, but I might be wrong. We both could be wrong. You have to work out your own solutions to that. And I'll tell you what, you guys can work it out. You just have to think a bit more, start writing, and look at all the possibilities, and you can definitely do it. You can make it slightly more complicated and increase and put another variable there. Let's put another person. Let's say D. And then think, put another condition, and see whether you can reformulate another problem or not from this. It will be slightly more complicated, but so these kind of things, we are not after their solutions. We are after only modeling them or writing them in this propositional logic form. We are not after precisely who got the prize and all that. Okay. This is just for brainstorming and nothing more than that. We will be after those precise connectives and all that, how we're going to write a proposition or statement or bunch of statements in terms of these logical symbols. This is how we feed into computer or feed into AI. They don't have brain of their own. It's how we design circuits and we do the programming and all that, and that's where we give logical statements and logical connectives. And that's how it works. Right, my answer for this is B and C are knights and A is knave. I might be wrong. You have to work out yours. Okay? So we'll meet again upstairs, room 205 at 2 o'clock. Until then, enjoy. All right, fellas, I'll see you soon.